So, is my screen visible to everyone?
Yes, sir.
So, my voice is also audible, right? No problem, no?
Yes, yes, sir. Yes.
Okay, okay. Okay, okay. Sorry, before we start, just a minute. Um, Stop sharing my screen, just a minute. So, what I want to do is, I will share with you the drive where I am, updating materials regarding this particular course. So everything from my videos to the PPTs, everything will be present in this particular drive. So just a minute, give me a minute. Okay, I'll share it in the chat box. So it's there. So those who didn't come to last week's class, you can access those materials through this particular drive. I will continue to update materials in this drive itself, and I'll post it every week. Okay, I mean I'll post this link every week so that those who are new or those who are missing, they can follow up the previous classes, and also they can look at the access the material that are available. Okay, so I'll also again give this drive link at the end of the class before we leave. So let's now go for the class. So does anybody have any doubts till now? From the previous classes.
Not now, sir.
Okay, okay. So we'll move on. So good evening, everyone. Today we are going to see about slip systems. Just a sec. Interruptions. Listen. Yeah. We will see about slip systems, crystal defects, and X-ray diffraction basics. So we will. I think we won't be having sufficient time to go into the problems. So we'll just see what are the basics of XRD, and I think hopefully next week we will start practicing the problems. So anyone remember what we saw in the previous class?
Yes, sir.
Ah, yes, yes. Ajit, you can tell. Yeah.
It's HCP and FCC problem.
So we saw about HCP. Oh, sorry. Okay. So we saw about HCP
HCP, FCP or BCC.
and FCC, like stacking.
Yes.
So stacking sequence we saw first. So we saw that HCP was AB AB and FCC was ABC ABC.
ABC.
So we saw what is the reason, right,
Huh. Yes.
for these two arrangements. Why it is arranged
Happening.
as it is. So that is one thing. Then we also got to see about the planar density problems. So we saw planar density problems for both BCC as well as FCC, right? In BCC we saw two problems. One
Two
is,
problems. Yes.
yeah, along the 100 plane, and another along
One
the
zero one. 101.
110 plane, right?
110. Yes. Yes.
Yeah, so these two planes, and uh, so we saw, like, sorry, not in BCC, FCC, sorry, BCC only. Yeah, 100 110. Yeah, these are the two problems we saw. And then along FCC also we saw in the 110 direction. So, does anybody know the formula for uh, planar density problems?
Number of atoms by area.
Yeah, that is the number of atoms divided by area of the plane, right? So this is the general formula, and this area of the plane will vary if it's a square or a rectangle. So we saw for the 100 plane, it was a perfect square when it comes to BCC, right?
Yes.
Whereas if it's a 110 plane, it
Rectangle.
was rectangle for both FCC and as well as for BCC. And
Yes.
we got to see like how to solve the problem if it is either FCC or BCC. So I think this is what we were able to see. After that, I think time ran out. Okay, so yeah. Um, in today's class, okay, this is just a summary. In today's class, we are going to see about the various slip systems that are in single and poly crystals. Before that, we will again look at the line defects like edge dislocation and screw dislocation in close up in detail, like why they are what they are. And then we will go for the surface defects. Okay, finally, we will look at the volume defects. That is, I mean, it's just a single picture only because it's hard to model volume defects theoretically at our stage. Like, in gate, they won't ask these problems. Finally, we will just go today. Only we will just see the basics, XRD basics, like what is XRD, how are X-rays produced, how are we getting the pattern. So that is what we are going to see today. We will see the XRD, the problems, the Bragg spectroscopy, and the problems, underlying problem, crystallite microstructure as a separate class in the coming week. So first, let us see the defects. Okay, so uh, defects usually arise due to saltification, right? So what is saltification? We have some pattern over here. Okay, okay, we call that pattern as a mold. Okay, and what are we going to do? We are going to take a cauldron. So here what we will have is we will boil it. Okay, and then we will melt the metal. Okay, so now we'll have molten metal in the ladle, right? This is fire. So this molten metal, what we will do is we will transfer from the ladle to the uh, mold such that we get a cast structure. Okay, so this is the casting of the molten metal. So when we cast it, right, when this metal solidifies from molten state to solid state, it will result in the formation of first atoms will group together, and when they group together they form nucleus, and when these nucleus group together they form crystals. Okay, and once these crystals grow they result in the formation of, sorry, um, once these crystals grow they result in the formation of grains. And then we know the grain grows and it forms a macro structure. So this is kind of what happens when the solidification process occurs. Okay. So here we can see, just a minute, we have the liquid metal here. So on solidification, you can see all the nuclei that is formed, and then slowly they start clumping together, and then we have crystals that are growing, and
Sir,
finally, yes, yes.
sir, they start coming together slowly or abruptly, like as I have studied that there is some minimum radius for a nucleus to be formed.
Yes, yes, yes. Yes, you're right. I mean, like when I say
Okay,
slowly means
but
it is,
they come
yeah.
abruptly or slowly. But this is a slow process.
No, no, sorry, sir. This is actually abrupt only. When I said slowly, I mean, I told out of, what can I say, colloquial saying, but you're right. It's actually abrupt. So the reason why it's abrupt is, when we are taking nucleus, it's a very small structure, atomic structure, okay? Atomic, or what can I say, nanostructures. So what will happen is, the surface to volume ratio, right? The S to V will be very high. So that means that these atoms are of high energy with free bonds. So because they are having free bonds on the surface, they will attract more and more atoms together. So they will quickly form these nucleus. I mean, these crystal growths. As they become bigger and bigger, as the surface to volume ratio becomes, what can I say, smaller. Okay, that is when the island becomes bigger and bigger. Island means the nucleus growing. Okay, if that growth becomes larger and larger, what will happen is, in the three-dimensional space, the volume becomes more, whereas the surface area becomes comparatively lesser. So as a result, the process begins to slow down when the grain structure starts to form. So that is the actual process that goes on over there. So I hope I haven't misled anyone by saying that, but it's actually a fast process initially. Then once it forms, grains, and the grain grows, that will be a slower process. So I hope I was clear, right?
Yes, sir, it is clear.
Yeah. Okay. As the nucleus begins to grow larger and larger, the SV, that is surface to volume ratio, it decreases, and as a result, the uh, grains grow slowly. The process slow down. Okay, right. Moving on. When we are doing the process of alloying, okay, so alloy means usually it is a molten mixture of two metals. By the way, does anybody know the difference between alloys and metal matrix composites?
So don't know about metal matrix compound.
You don't know about metal matrix composites? Yes, yes.
सर जो मेटल मैट्रिक्स कंपोजिट होते हैं इनमें रॉड के फॉर्म मतलब उस तरह आइसोस्टेन आइसोस्ट्रेस वाली कंडीशन वाली के ना.
Yes, that's actually a good point. You have isostrain and isostress condition here. Okay, sorry, isostress.
All the foreign metals particle are मतलब किसी में पास पास हो तो कुछ इस तरीके से.
I'm sorry. Can you repeat that?
मतलब he means to say that that won't be an homogeneous way.
Exactly, exactly. So the
आ रहा था बिल्कुल.
whole point of isomeric property is that the due to non-uniformity, the stress is somewhat distributed instead of a particular direction. So yeah, you have a very good point right there. But there is another key difference that separates these two. Does anybody know that? Okay, I'll explain.
Sir,
Yes, yes,
would
Arjun.
it be on bonding distance or like that?
No, no, no. Like, it's not a very complicated thing. It's actually quite simple. Okay, I'll explain. The thing is, alloys, if we take to say, um, let's say zinc and copper, na, what will happen is you will have something known as phase formation. So we will discuss in detail regarding the phase formation in the coming classes. So you will have different phases at different temperatures. Whereas when you take a metal matrix composite, it will have, like, it will retain its phase at all temperatures till it is melted. So this is the key difference between these two things, like alloys and metal matrix composites. So coming here, the process that we are doing is alloying over here. So alloying means, we are mixing molten metals, two molten metals together, and we are solidifying. So during the solidification process, one of these many defects will occur. We already saw these point defects. So what we are going to see here now is, because of these point effects, what sort of force is acting on the lattice plane. Say for example, we take this point 1, right? So here there is a vacancy. Due to vacancy, there is a compressive force acting in this particular area, right? And this is pretty high. So if you see the arrow marks here, if they are larger, that means the force is larger. And if you see that the arrow marks are smaller, it means the forces acting are smaller. So then let's come to number 2. Here there is self-interstitial. So self-interstitial means the same atoms, they are occupying some interstitial position, and that is causing some force in the crystalline lattice. The third is the interstitial impurity, that is external impurities that we are giving. If that comes and occupies a position on the lattice, that is interstitial impurity. The fourth and fifth are substitutional impurities. So any atoms whose size, atomic radius, is almost similar to that of the original, the uh, solvent material. So that it will result in a substitutional impurity. And of all these impurities, we see that the least distortion is caused due to interstitial impurity as compared to everything else. So this could be a possible one more question. You can note this. So this we already saw, like what are the types of imperfections. Okay, now coming to line defects. So we have a crystalline lattice like this, okay, and a plane is inserted. Usually these line defects or dislocations don't happen just because some plane is inserted just like that. This is due to shear stress. So when we give shear stress, what will actually happen is certain bonds tend to break, and when that bond tends to break, there will be an extra half plane. So what will happen is, when more and more shear stress is given, what will happen is they will tend to move in a particular direction, and what will happen is this bonds, right? What will happen is, when they move, uh, they will like attract nearby atoms. So they will kind of what can I say, uh, keep moving until this lattice comes to a halt. Okay, you will see the mechanism in the video that is coming, and we must understand that this particular line over here, okay, that is called the edge dislocation line. Okay, this line over there. Okay, and that is always perpendicular to the Burgers vector. So this is the Burgers vector, and the edge dislocation line is this thing that is always perpendicular to it. Next, here what we have is, this is actually screw dislocation. So screw dislocation is uh, in this direction, okay, like a twist. What is happening is, in the front of this particular cube, okay, for about one atomic space, there is a twist in the crystal lattice, whereas here there is no change at all. So if here we see, this is the screw dislocation line, and the screw dislocation line is actually parallel to the Burger vector. So this is what is happening here, and usually the dislocation occurs along a plane. Okay, it occurs along a plane called the slip plane, and yes,
In screw dislocation, where was the line in the 3D structure?
screw dislocation line. No, here it's actually this line.
First one.
Yeah, yeah.
Okay, sir.
So that is always parallel to the Burgers vector. So here the dislocation line is
So,
along. Yes.
so actually, I'm telling, would it be visible on a Rubik cube, like the screw dislocation?
On a Rubik's
I
cube, you're
mean,
saying.
if I twist it, yeah, if I twist it.
It is, yeah, you can visualize it in a Rubik's cube, but it won't be very accurate. But yeah, you can visualize. Yeah, that is no problem.
Because, yeah.
Yeah, of course you can visualize that. No problem. That is correct. Yeah.
Sir, as we cannot differentiate between slip and no slip plane in the Rubik's cube, so how can we visualize it?
No, no. Actually, what I'm saying is just the motion. See here the dislocation exactly one atom distance, one atomic distance. So of course in the Rubik's cube you can't see so accurately. But the one problem in Rubik's cube is the whole plane will like shift.
Yes, sir.
That
Layer.
is the one problem. Yeah, here only half
Huh.
is there. Like there's a certain boundary to it. So it's a little difficult, but for beginner's sake, you can kind of visualize it, but you can't perfectly visualize the dislocation, screw dislocation in the Rubik's cube. Uh, but just for like imagination purpose, you can just do that. But that is not a perfect visualization.
Okay.
Yeah. So if we look at this plane, um, we see that this is a extra half plane developed because of the shear stress. Okay, the bonds are broken, and there's just this extra half over here. And then as we give more and more shear stress, these bonds tend to move, and as they come closer to the next set of atoms, they tend to latch on, and it becomes like this, and then it just keeps moving until the extra plane is outside. So I hope you guys get it. I mean, I'll show a video, so in that video it will be clear, but till then I'll try to explain. And also, a useful way to describe this dislocation is to use a Burgers circuit or Burgers vector. Actually, the in that vector the whole thing is called the Burgers circuit. So it is an atom to atom path taken in a crystal, which forms a closed loop. So the thing is, like, here there is a massive dislocation. So this Burger vector will trace the line where dislocation is absolutely minimized, because beyond this point we see that there is very minimal dislocation, right? So tracing that line, for tracing that area, we use this Burgers vector, okay, or Burger circuit. Here it's Burger circuit. So it also describes the size and direction of the main lattice distortion. So in another place what I read is Burger vector is also the dislocation size, or the size up to which the dislocation is moving. So if this is the Burger vector, means say round about this distance now, it is the like dislocation size, we can say. But there are better approximation methods, but as of now, like, this is one of the most primitive method. So again, the same thing, right? What we saw, the Burger vector is perpendicular to dislocation dislocation line in the case of edge dislocation, and Burger vector is parallel to the dislocation time in terms of screw dislocation. So next is,
Sir,
yes,
sir, in uniaxial tensile loading,
uh,
मतलब ये दिस इज डिसलोकेशन मोशन को इस तरीके को 45 डिग्री पे करके हमें समझना होगा ना.
okay, okay. You're saying about the CRSS, right? So what happens is when we give the uniaxial tensile stress, um, there will be a 45-degree dislocation. So you're saying that only, right?
सर मतलब मैं आई वाज आस्किंग दैट दिस डिसलोकेशन मोशन विल बी अलोंग दिस 45 डिग्री लाइन ना सर.
Yes. I mean, in case of single crystal, yes. So it will usually be along this 45 direction. We'll come to that actually. We are going to come to that very soon. But this is like at a atomic scale. The screw dislocation and edge dislocation, they are more to be visualized at the atomic scale, whereas the dislocation that you are talking about along the 45-degree angle, so that is at a macro scale. You can visually see it actually, and for single crystal it will be like perfectly visible. So we'll come to that.
ओके.
Yeah. So these are the dislocations. Um, Say we have a HCP crystal structure here, AB. So what will happen is, after we give some tensile stress, it changes. So sometimes what will happen is this HCP can also become some other unit cell like FCC. The structure completely changes after tensile loading. So this is in some cases, okay. What one example is magnesium. So magnesium, before loading, it will be in HCP structure. Then after tensile loading and some heat treatment, it will become like FCC structure, and it will be easily deformable. And by the way, when it comes to deformability, FCC is easily deformable. Uh, sorry, yeah. Then HCP, it is even more hard to deform, and BCC is hardest to deform. So we can't deform it, like it will just crack and it will break immediately. So this is usually the pattern, but FCC means it will easily deform and it will easily uh, be able to drawn into wire, or it is malleable. Then we have a condition known as twinning, twin boundary. So usually this twin boundary occurs in HCP structures. So what happens is, we take a HCP structure like this, and if we give some sort of a tensile load, okay, at one particular point, what will happen is there will be a sudden deformation, and after a particular distance, what will happen is this structure over here will be repeated on the same like on the other side. That is, they will look like twins. The atomic arrangement will be similar. So this will be within the crystal, a single crystal. I mean, I'm not saying single crystal, I'm saying if you have a polycrystalline material, okay, and then they undergo stress, at that time what will happen is you will have sudden uh, deformation, where in the middle there will be a boundary like this, and then on both sides you will have a lattice arrangement which will be like mirror image to each other. So this condition is called twin boundary or twinning effect. And these are all, so far what we saw were uh, line defects, and this is somewhat area defect, and this is bulk or volume defect. What you see here is a giant crack. Cracks, pores, then holes, all of these are, sorry, all of these are volume defects. Okay.
Are these twin boundaries?
Yes.
These blowholes and cracks are yeah, twin boundaries.
No, 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 no. These are different. These are volume defects. So twin boundaries are here. So these cracks and blowholes, they aren't caused due to any atomic variations. So these are caused due to some major errors. So these are like macroscopic defects.
Okay.
So usually when we have these sort of twinning or any other defects at the atomic scale or the micro scale, they usually are beneficial. Whereas beyond the micro scale, right, then it is usually non-beneficial to the material. So all these bulk and volume defects are usually non-beneficial to the material. So next we will come to the critical resolved shear stress. So for the dislocation motion to occur, okay, the resolved shear stress should be greater than the critical resolved shear stress. Okay, and actually the critical resolved shear stress, it is an inherent property of the material. So every material has its own CRSS, and whenever the resolved shear stress, okay, that we will see in the next slide. Whenever that resolved shear stress, that is tau r, is greater than the material's CRSS, then it is bound to break. So it will result in deformation, and that too, the deformation will usually be at a 45-degree angle, and the deformation will always be along the slip plane, and specifically in the slip direction in that particular slip plane. Okay, and here also you can see the dislocation, how the dislocation is occurring as the tensile force is kept on being applied. So these are the several processes, be it rolling, be it extrusion, be it drawing. For everything, no matter what the external force is, no matter what type of the external stress is, okay, there will always be a shear stress that will be acting on the material, which will cause it to deform. Only shear stress will, sorry, cause it to deform. Yes.
How to identify a slip plane?
Slip planes, they are usually identified by planar density. So what we do is, we first find, okay, where do I write, okay, right here. So to identify the slip plane, you have to find the planar density of different planes of a unit cell. Say for example, in the previous class we discussed, right? We write, okay, I'll just write here. So in the previous class, what we did was, we discussed regarding BCC. Okay. So for an example, we solved BCC along the 100 direction and 110 direction. Sorry, 100 plane and 110 plane. So when we tried the 100 plane, okay, so resulting we had, it was like a square, and we had one atom and the area. So this is nothing but A, which is 4 by root 3 r. Okay, that we would have seen, no, in our problem for solving BCC, right? For getting the lattice parameter from the radius of BCC. So that will come here, 4 by root 3 r. So here it's a square, area square, so r square. So roughly, if we take iron at 912 degrees, it will be BCC. So the radius is around 0.1732, I guess. Yeah. Nanometers. So we'll get the answer of approximately around like 1.2 into 10 power 19 atoms per meter square. Whereas if it's 110, we will get something like this, 3 by 8 root 2 r square, and the answer was something like 17.22 into 10 power 19 atoms per meter square. So here in 110 plane we have more atoms compared to the 100 plane. So this could be the slip plane. So based on which particular plane has more number of atoms compared to the other plane, that will be our slip plane. So here also we have the definition. Slip planes are plane with the high planar density of atoms, and slip directions are the lines with the high linear density. So you get the point, right?
Yes, sir. Yes, sir. Sir, I want to ask another thing that in a crystal, as there are grain boundaries,
Yeah.
uh, मतलब grain boundaries के along why the motion or the deformation happens along the grain boundaries along the
So in the grain boundaries, what will happen is there is free space. There is some,
free space, so
yes,
density is less.
and yes, density is less. Exactly, lesser density. Also high energy. So this will cause heavy dislocation along the grain boundaries. And not only that, there should also be cross slip. Cross slip means slip of one grain should coincide with the slip of the other grain, so that they will all come together and result in the failure of the material. In case cross slip does not occur, no, in that case the material will be strong. Say for example, if this is the slip plane and the slip direction of one particular grain, and for another grain it is in this direction, then they contradict with each other. So there is no movement, like the force is not, the dislocation is not transferred across the material. As a result, what will happen is this material won't fail easily. So only if cross slip occurs, there will be easier failure of the material. Otherwise, we will have to give more stress for the material to fail. Uh, was it clear?
Yes, sir. Yes, sir.
Okay.
Sir, since
Yes.
along the grain boundaries,
Mhm.
the density is less, so why it act as a slip directional plane like that?
Um, actually, as far as I know, the directional plane comes from the, what can I say, uh, density of the particular uh, plane. Like say for example, if we have a FCC, so or I think here in FCC, the 111 plane is having most number of atoms. So the deformation will be along this direction or in this direction. So the direction where majority of the atoms are present. But I do not know about the grain structure as to why deformation. My guess is because there is more space there, it is acting as a you know uh, place for slip, region of slip. But I'll verify and I'll let you know. Okay. So why the grain boundaries act as slip planes? Sure, I'll verify this and I'll let you know. So meanwhile, my guess is because of the space that is here. Um, yeah, and also in the SIP system, uh, it is a combination of a plane and the direction. So this whole region we take now, this is the slip system because it consists of both the plane and also the direction. And it's not just this particular plane. Okay, there will be similar planes also. We also know, right, family of planes. When we include the entire family of planes, then we get the slip system. So entire family of planes, then we get the slip system. Okay. Yes, did someone want to say anything? Um, Okay, moving on. Yeah, again we saw all the definition, right? What is the slip? Process by which dislocation moves and deforms, the direction, and then the plane, then the slip system. We saw this. Again, we saw the slip plane is the plane having most dense atomic packing and greatest planar density. They both mean the same thing. Greatest planar density means most dense atomic packing in that particular plane. And also, dislocation distort the lattice and makes it soft and malleable. Hence, they affect the mechanical properties. As I had mentioned earlier, right? In magnesium, initially it is HCP, then on tensile stress, it becomes FCC. Then we have surface imperfection. So this surface imperfection may arise due to two grains or smaller crystals within a larger grain, that is polycrystalline material especially. Polycrystalline material means you already know it is multiple grains or multiple crystals. So the rows of the atoms may run in slightly different direction. Okay, so this mismatch usually increases the strength of the material. If no mismatch, then it will result in cross slip. So cross slip means, as we already know, it is easier failure. So let's just see the dislocation movement video. Please let me know whether the audio also is coming.
We will now look at an edge dislocation. This
Is
is
the
a
audio
commonly used model of a lattice called simple cubic.
coming for all?
Using this simplified lattice, we can
No,
understand the
sir.
basic principle of an. We will now look at an.
Audio is not coming, is it?
No, sir. Audio is not coming.
Just a minute.
We will now look at an
Is the audio
edge
coming now?
dislocation. This is a commonly
No,
used
not
model
at
of a
all.
lattice called
Okay.
simple cubic.
Last time it was coming. What happened? Screen. Okay. Just a minute. Okay, guys, my computer is stuck. Just a minute. What happened to the audio? Okay, I'll stop presenting. Just a minute. Okay, now I'll just present the tab. Sorry, not tab. Present the window. Is my screen now visible?
Yeah, your
Yes.
screen is visible.
Is the slideshow PowerPoint visible, like in slideshow mode?
Uh, yeah.
Okay, now I'll play.
We will now look at an edge dislocation.
Is it coming now?
This is a commonly used
Very
model of a
slightly.
lattice called
Slightly.
simple cubic. Using this simplified lattice, we can understand the basic principle of an edge dislocation. When a shearing force is applied to the lattice, a plane will try to
Is it
find a
coming?
new plane to bond with in order to
Very
relieve the
slightly, sir.
tensions
Like
in the
they are
lattice.
telling
The
it's
plane that has been
coming.
released will then be without a
Okay.
bond.
But is the
The
video
line
playing?
this
No
occurs
problem,
along
right?
is called the dislocation
No, no, no,
line
not at
or
all.
edge.
It's also black.
If the dislocation
Dark.
continues, the dislocation will eventually.
Okay, in that case, I'll just share my screen itself. I know last time it came perfectly, so I know what's wrong this time. Okay, once again I'll share my screen. Okay, the video is available in that link, so you can play it in your free time. It's under video resources. So as of now, you can just see the video, the plain video. I think that itself will be kind of understandable.
Okay.
Yeah.
We will now look at an edge dislocation. This is a commonly used model of a lattice called simple cubic. Using this simplified lattice, we can understand the basic principle of an edge dislocation. When a shearing force is applied to the lattice, a plane will try to find a new plane to bond with in order to relieve the tensions in the lattice. The plane that has been released will then be without a bond. The line this occurs along is called the dislocation line or edge. If the dislocation continues, the dislocation will eventually leak out into the grain boundary. In a real lattice, the planes and directions are not as easy to identify as in a simple cubic lattice, but the principles are the same. We will now show you an edge dislocation in an FCC lattice. This is how local HCP form in the FCC lattice, and is the principle of how deformation in metal occurs.
Okay. So I heard that there's no audio. I'll repeat this video and I'll explain once again. Okay. So what is happening here is this is edge dislocation. So here initially the atoms are present as they are, and just for our convenience sake, they have given one extra pair of atoms. Now, when they are giving shear stress, what is happening is that pair of atom is debonding, and then it is moving. Okay, and then when further stress is given, it will be moving from one place to another, and the bonds will release and reattach based on the stress that is given until and unless it reaches the other side and the dislocation is stopped. Then what is happening is the structure that you see over here is an FCC structure. On dislocation, it is becoming a HCP structure. So as I mentioned earlier, in some cases this happens. That is, especially I told you in magnesium, right? In magnesium, the opposite. HCP structure on like dislocation becomes FCC. So likewise, this is the like on dislocation. Next, we will see. Yes.
Sir, in case of magnesium, you told that Hc become FCC. If the loading condition are reversed, then will it become again HCP?
Loading reversal, right?
Yes.
Loading reversal. You mean like compressive loading?
Yes, sir. Yes, sir.
Compressive loading. Usually, no matter what the loading is, shear stress only will be acting, like be it compressive or uh, like tensile. So I believe it will still like convert like from HCP to FCC only. I don't think it will go the other way around. Anyhow, I'll verify and I'll let you know that.
Okay.
So you asked two doubts, right? One was regarding the grain, as to why grain boundaries are regions for slipping, and then another thing is this thing regarding the HCP. this whether HCP can be reversed back to FCC on loading. So now we will go for the slip. Okay. So single crystals, they are easy to treat and easy to study. So due to several studies on this single crystals, every single time when they applied some sort of a load, be it a tensile load or a compressive load, it always used to deform at a 45-degree angle. That's what they have observed. And then they came to the conclusion that the applied stress irrelevant of what it is, the dislocation occurs due to a shear stress. So that was their final conclusion after they observed this thing on a single crystal. Okay. And this is a microstructure, like under a microscope, if you would look at a single crystal optical microscope, you can clearly see the dislocations along a 45-degree angle. So now let us look at the resolved shear stress. Okay, as we already saw, for a dislocation to occur, the uh, resolved shear stress, that is tau r. Okay, this is resolved shear stress tau r, should always be very much greater than the CRSS. Okay, so as we know, while we are applying a tensile stress, the tensile stress is equal to the force divided by area. Right, that is our usual formula. But what is observed is slip is happening in some other direction and not in the longitudinal direction itself or the lateral direction. Right, it is occurring at some angle. So we will call that particular direction as a slip direction. Right?
Sir, sir,
Yes.
the slip direction will not be like this, as it will be forming a like cone structure, sir, cup and cone structure.
Oh, yeah, yeah.
So why we are considering it as a only a slice?
Oh, no, see, actually, this is in terms of a single crystal. A cup cone structure usually forms, I believe, in a metal that too like polycrystalline structure, right? So this is a single crystal. So usually, when deformation happens in single crystal, it will be in this 45-degree direction.
सर 45 डिग्री शुड बी फ्रॉम ऑल द पर्सपेक्टिव, मतलब अलग अलग साइड से देखेंगे वहां से 45 डिग्री होना चाहिए.
Sorry, all direction means I don't understand.
मतलब सर हिंदी मतलब इंग्लिश में बोल नहीं पाया.
It's okay. Uh,
मतलब सर जो कोन है ना, कोन जो है उसको कहीं से भी देखें वो हर बार
मतलब सर फ्रंट
45.
व्यू, साइड व्यू और टॉप व्यू और लाइक
नहीं
दैट.
टॉप नहीं रे,
okay.
मतलब जो
Yeah.
मतलब कि जो कोन होता है उसको कहीं से भी देखें, उसका जो एज है
Mhm.
वो 45 डिग्री हॉरिजॉन्टल के साथ एंगल बनाता है सर. तो इसीलिए ही मतलब वो एक परफेक्ट, मतलब मुझे ऐसा लगता है परफेक्ट रिप्रेजेंटेशन है कि 45 डिग्री पर होता है उस चीज के लिए. पर इस वाले केस में हम केवल ये शो, अगर हम अपना पॉइंट ऑफ व्यू चेंज कर दें तो 45 डिग्री शो हुई नहीं होगा वो सर, और दूसरा एंगल बताएगा. मतलब ये बात बोलना चाह रहा था.
भाई तू क्वाड्रेंट के सिस्टम में बोलना चाहता है क्या?
नहीं मतलब उसको कहीं से भी देखें, मान लेते हैं
हाँ
रॉड हमारे सामने है तो
तो
45 डिग्री तो कौन ही बनाएगा ना, कहीं से भी उसके
हाँ
चारों तरफ देख लें.
हाँ
पर इस वाले केस में जो एक स्लाइस बनाया है, ये केवल एक पॉइंट ऑफ व्यू से ही 45 डिग्री बताएगा.
Yeah, so that is the thing. So I will check whether it is different for polycrystal and single crystal, and that too like metal, because in metal you will have this cup and cone formation, whereas if it is some brittle material, say composite or ceramics, usually it will be somewhat I think in this particular 45 degree like break, sudden fracture instead of cupping and cone formation. So since here they have taken a single crystal, Single crystals usually are very weak. So I believe because of this weakness, this sort of deformation is occurring. But yeah, I'll again verify whether this cupping and coning is because it is a polycrystal, or is it an inherent phenomenon of the metals? Is bro?
भाई वो ब्रिटल में 45 पे इसलिए नहीं होता है क्योंकि ब्रिटल का जो वीकनेस होता है वो टेंसाइल में होता है, shear में नहीं होता है ब्रिटल वीक.
Hmm.
Yeah, yeah, there will be tensile break like this itself. No, like we can't predict sometimes. Sometimes it will be like tensile fracture. Uh, Depends on where, like the stresses are acting, right? Where the maximum number of atoms are there, so accordingly the breakage will happen. So of course I'll re-verify this as to why, like here there is cupping and coning, and then while in single crystals we are having this sort of deformation. And for all single, does this is this applicable for all? I will just check and let you know.
Okay, sir.
Okay, so um, let me just re-verify your questions. I'll note it down. First is you want
Slip across the grain boundary
yeah, zip across grain boundary. Next is
on
HCP,
reversal of load.
FCC to HCP on reversal, right?
Yes, sir.
Reverse loading, and then the slip direction,
Yes,
uh,
sir.
cup and cone formation.
Slip direction will be conical. The slip plane will be conical.
Okay, slip plane, is it cone? Okay,
Yes, sir.
so I'll just verify and I'll let you know.
Sir, would it be cone or elliptical, sir?
Uh, Elliptical means the cone will be like this. Elliptical will be
Huh.
more like rounded like this actually. You'll have rounded edge.
Huh.
Uh,
So,
Usually it will be like cone only, because elliptical means it will be, what can I say, rounded on all sides. Cone means you'll have that taper, that perfect taper will be there. There will be some sort of taper.
huh.
In elliptical, there will be very minor taper. Cone, you'll have a larger taper. Usually, it's as far as I know, a cup and cone only. Like there will be a cup, and then there will be a cone formation.
Okay.
So, as far as I know, ellipse doesn't usually happen. Okay, coming to the thing. So along the slip direction, right? Um, there is a force acting. The force is acting along this direction, and then this is the area, and then normal to the area is this. That is slip plane normal. Here, area is at angle, like say longitudinal, along the longitudinal direction, but this area is some sort of an angle to the main area. So this is the slip direction, and the shear stress usually acts across this particular area despite the force that is applied. Okay, so we know that the general formula for stress is force by area, right? So for tensile stress, this is it. For shear stress, it is shear force by shear area. Okay, and then if we relate these two together, right, what will happen is we are trying to relate this force with shear force. So this force is at an angle of lambda, right, from the tensile force. So it is F cos lambda, and the area that is being sheared is A by cos theta. Okay. So when we substitute these two, I mean these two values in this equation, we get f cos lambda divided by A by cos theta, and this f by A is our longitudinal stress, and then we have cos lambda over here, and then this is 1 by cos pi, right? So that will become that is in reciprocal, and that will come to the numerator. So we'll have sigma cos lambda cos pi. So this is the formula for resolved shear stress. Then the condition for dislocation motion to occur is, we got the formula, right? Sigma cos lambda and cos phi. So if the lambda is 90 degrees, then we get cos 90, and cos 90 is equal to 0. And if the force is in the lateral direction, then lateral means lateral to the main force, tensile force, then cos 90 is equal to 0, and as a result there is no stress acting on the particular material, so there is no deformation in the lateral side. Same time, along the longitudinal side, okay, let us consider here when the stress is acting, cos phi will be 90 degrees. So cos 90, where this is phi, is 0. As a result, again the whole thing becomes 0. So there is no stress acting along the longitudinal direction also. Whereas if we now put 45 degrees, right, sigma into cos 45 and cos 45, this is lambda and this is phi, what will happen is we get sigma into 1 by root 2 into 1 by root 2. So we get sigma divided by 2, or for the tensile load applied we get 2 into the resolved shear stress, 2 times the resolved shear stress. As a result, there is failure in the longitude, this 45-degree direction. So this is how they were able to kind of conclude that usually the deformation occurs in general along this 45 direction plane. And we also saw, right, for different structures, like what are the number of slip system, and why the critical resolved shear stress for each, and what will happen to the material because of that. So if we see some random case here, the polycrystalline crystals are completely disordered. So since they are disordered, cross slip does not occur, and as a result this material will be strong. Whereas here we see that almost all the planes are almost aligned to each other, so easy chance of cross slipping and material failure. So here we have for FCC, there are 12 slip systems, and for BCC there are 48 slip systems, and for HCP there are only 3 slip systems. So sometimes they will ask like why, you know, not why, but what is the number of slip system for FCC, for BCC, and for HCP. So of this we can see that BCC has the highest CRSS, so it is almost around 1 ton. So yeah. Next we have the external surface. So we think we already discussed this. If you have an external surface, that is surface to volume ratio. On the surface, energy will be more due to compared to the bulk. As a result, what will happen is the material will try to minimize the surface areas. That is something coming in contact with it, say like a liquid. When it comes in contact with it, the free bonds on the surface will try to bond with the liquid. Okay, and as a result, the liquid will spread against the surface tension. Next, the grain boundaries are regions between the two grains. So that's what we see over here. These are the grain boundaries. They are uh, slightly disordered or sometimes highly disordered also. As we know that low density of atoms are there, as you can see very clearly. As a result, what is happening is you will have high mobility. So here they have mentioned high mobility means, I think, easier chances of slip. And high diffusivity, meaning easier chances of impurity entering the material. That is, the impurity that are entering can easily be stored in this grain boundary regions, and as a result, since there is free movement of atoms inside and outside, diffusivity, right? So since there is free movement of atom inside and outside this grain boundary, you have high chemical reactivity. So this is grain boundaries. Then we have tilt boundaries. So tilt boundaries are within the grains. So they are usually two misaligned grains appearing as an array of edge dislocations. Sorry, two grains, right? Not a single grain. So it will be somewhat like this. If there is a single dislocation, then we call this edge. There is, if this there is an array along a line, you have multiple edge dislocations, that becomes a tilt boundary. So multiple edge dislocations, and the rotation axis is parallel to the boundary plane. So I believe this is the axis of rotation, and it is somewhat parallel to the boundary plane. Sorry, it is parallel to the boundary plane. Whereas for twist, the low angle grain boundaries appear as an array of screw dislocations. So instead of edge dislocations, I believe if we have screw, it will be like this. It's a little hard to draw it actually. So these are screw dislocations, and the rotation axis is perpendicular to the boundary. So I believe the boundary, it will keep extending in this direction, whereas rotation axis will be in this direction. So it is at a 90-degree angle. See, this is a bit hard to visualize. I'll try to get a video for this, for twist boundaries. And twin boundary we already saw. So if there is a, a sudden fracture twin, one side will be equal to the other side. So even this is not a good representation, but usually if you see in the microscope, if this is a region of twin, you will see that one side is will almost be the mirror image of the other side. So that is the twin boundary. And twin boundary usually occurs on HCPs. Then there is stacking fault. So stacking fault occurs if one of the set of atoms are missing. That is, instead of just one atom, if we have a whole plane completely missing, then we will have a stacking fault. Okay. And then surface energy we already saw, like what happens, to reduce the surface energy, the liquid droplet just expands against the surface tension, and finally, it covers the whole surface area of the metal. So then we will see the importance. So defects play an important role in controlling the mechanical property, like okay, interfering with the slip and strengthening the material. Like in case of twinning, it actually strengthens the material. That is, it causes strain hardening before failure. Likewise, ceramic and polymers have relatively less effect due to defects in comparison to metal, because they have more porosity. See, ceramics and polymers, they are actually sometimes like ceramics are somewhat uh, crystalline, like they'll be amorphous also, but polymers most will be amorphous, but there are some crystalline polymers, and to grow crystalline polymers it is like very difficult. um, so what will happen is, these sort of defects that we studied about usually have a greater role on metals. For studying polymers and all, like that's a completely different story. And since they have more porous, I mean, since ceramics are more porous, they are discontinuous, so crystallinity is less because of discontinuity in ceramics. Then strain hardening, again we saw, right? Strain hardening strengthens the material by deforming it, which increases the dislocation density. So initially when material undergoes tensile loading, right, there will be, there is loading, then it yields, then it undergoes strain hardening, and then finally it undergoes failure, right? So this strain hardening is due to dislocations. Then point effect can have a dramatic effect on the optical, magnetical, and electrical property of the materials. So that it's actually entirely material science. So the point effects such as Schottky, Frenkel defect, they can be used in electronic applications such as smartphone uh, displays, touchscreen displays. So primarily uh, the effect is due to ion migration, and that ion migration happens due to point effects as we move the screen. So the mechanism is even more intricate, but I'm just explaining in general like what happens. So in semiconductors, the dopants are critical to achieve the desired performance. Like we already know, right? P and N type semiconductors. So based on dopants, we will have, if it is 3 valence means trivalent means it is a P type, pentavalent 5 means it is a N type semiconductors, and we all know that N type usually performs better than the P type. Then for an atom, addition to glasses change its color dramatically. Have you guys heard of this stained glass? Has anyone heard of it?
Yes, sir.
So stained glass means, does anyone know like,
Color.
yeah,
Look, there would be different variant of colors, like displaying different variant of colors or pixels.
exactly. Usually if you go to the churches means you will find that on the walls,
Ah,
on the everywhere ceiling or walls, you will have these windows which are having some drawings with the glass of different color. Do you guys know how the color comes actually? By mixing what element?
no, sir.
Usually during the olden times they used to mix gold nanoparticles. So gold at different uh, nanometers, right, give different colors, optical property. So because of this, you used to get different colors on the stained glass. So as far as I know, I think if it is 20 nanometer, I think it may be red, and if it is around 40 nanometer, it will be around it will be violet. 40 or 60, I don't know. So something like that. At different nanometer, it will give a different optical property. That is, it will give different color. That is how you used to get the stained glass. So that's why foreign atom or ion addition changes the color dramatically. Again, these are what we saw already. Okay, now we'll just quickly go through XRD and we'll finish in within few minutes. So the history of X-ray, I think most of you would already be knowing that X-rays were discovered by this person, Wilhelm Conrad Röntgen, and he won the Nobel Prize for that in 1901. So this was the first X-ray that was taken of this person's wife, Bertha Röntgen, and this is the modern radiography. So there's a significant difference, improvement, right? Then these are just some basics of X-rays. So they are electromagnetic radiations, and they have very small wavelength compared to that of the visible light. So below X-rays we have gamma radiations. So anything below visible light is very dangerous to health. I think you will already be knowing this. So all of these are electromagnetic radiations. So X-rays come between the 0.01 nanometer to 10 nanometer spectrum. They are of high energy, okay, and they are very penetrative. So anyone know why they chose X-ray instead of gamma ray or ultraviolet rays for XRD?
Sir, even sometime in non-destructive testing we use gamma rays as well.
Yeah, sometimes we use, but mostly to confirm a crystal structure, right? They always use XRD. Does anyone know why? It's a standard, like
Sir,
for us, it's a
to
standard test.
to getting the accurate result as the I mean the wavelength are like I mean the wavelength are homogeneous or same, like don't
Ah,
oscillate that much like gamma ray or
the thing is, you're right when you said wavelength. So the wavelength of X-rays will be close to interatomic distance. So interatomic distance means they are in the range of angstrom to nanometer, right? And X-rays come perfectly in that particular range. Sorry. As a result, we choose X-rays for determining crystal structure rather than any other method. So I think it's already too much time. It's 8:30, I guess. So I think we'll stop with here. From next class onwards, I think we can go for the other things. Is it all right?
okay.
Yeah.
Yes, sir.
Sure. Thank you guys for joining.
Thank you,
Again,
sir. Thank you, sir.
yeah, thank you so much, guys. Thank you. And again, I will share the that link. Just a minute. Computer is stuck. Yeah. So those who didn't attend my previous classes, you can go through that link and you can get to know what was discussed. And I'll continue to update all the further materials or even the recording of my video here in this particular link also. So you can go through it in case you have missed the previous classes. So thank you once again, guys. We will
So,
meet again.
so,
Yes, yes.
I've noticed that your voice is breaking in between the classes. The last class also it's breaking. So, is it for me only or
Oh, okay. Oh, is it for others? Was my voice like breaking?
um,
No,
uh,
sir.
it's
No,
like
sir.
pulsating?
Okay, okay. No, no. I was asking whether for others it was breaking. No problem. So in that case, you can log into this particular link that I have shared, and you can view the previous these things recordings. So
Okay,
even this
sir.
recording, I will upload there.
Okay, sir. Thank you, sir.
Sure. Thank you so much, guys. Yeah, we'll meet next week.
Okay, sir. Thank you, sir. Good night.
Thank you, guys. Yeah, bye.
Thank you, sir.
Hello? Hello, sir?
Yes, yes, Sarthak.
Sir, I have a doubt, sir. Sir, what is the difference in matrix composite and ceramics, sir?
You mean metal matrix and ceramic matrix?
Yes, sir. Metal matrix composites, sir.
Yeah, Oh, you mean metal matrix and alloys?
ये हाँ सर, मतलब मैट्रिक्स कंपोजिट सर, मतलब होता क्या, डिफरेंस क्या है सर? मतलब मैट्रिक्स वर्ड यूज होता है ना सर कंपोजिट में, उससे मतलब कितना चेंजेस आ मतलब?
No, no. Actually, they both are same only. Like composite means. Actually, the thing is, matrix is your what can I say? Solvent element. Solvent means that is the majority of the composition, and the solute is the minority of the composition you are adding. Say, for example, if you have metal matrix composite means the matrix, that is the solute, that is the majority element, will be metal. If it is ceramic matrix means the majority of the element will be ceramic, and then the solute that you add can be metal or can be ceramic also. Usually if it is purely ceramic that you are adding to the ceramic matrix, it is called ceramic matrix composite. If you add metal, little bit of metal, then it's called CERMET, CERMET. There is a
Okay.
combination of both.
Okay, sir. Thank you.
So you got the idea, right?
Yes, sir.
Matrix means which component is majority. If metal is majority means then it is metal matrix.
Metal matrix. Okay, okay, sir.
Yeah.
Oh, thank you, sir.
Thank you, Sarthak.
So happy New Year.
Happy New Year, everyone. Thank you for wishes. So you got the link, right, Rahman?
Yes.
Okay. Okay then. Thank you. See you guys. Bye.